So now, finally, I see the little red dot and we're recording. Okay, so the next thing, of course, that I'm going to do, and this is what reminded me that I wasn't recording, is we are, of course, going to do a little visual aid to assist my blathering. And that visual aid will come in the form of some slides that I'm going to present. So I'm going to present my entire screen, as I usually do, and then I'm going to click on this thing, and it's going to allow me to do that. And then I'm going to hit down here, I hope. And this is exactly where we happen to be. Here. So just like I talked about the Earth pulling you towards its center, now we can translate the field of gravity into the electrical field. And I have a bunch of lines here I've marked with E's that are telling you what a charge field will do to another charge. Now remember, gravity works on masses, but charges work not on the mass of the thing in proximity to it, but on the charge of the thing in proximity to it. If you have an uncharged neutral mass, it may not experience any attraction in an electric field. Now, notice I use the word may not. It can be induced to be attracted to the field. How can an uncharged object be induced to be attracted? We talked a little bit about this on Wednesday. If the material is a conductor, conductors allow charge to flow in them. When you put a neutral object near a charge, and if it's sufficient charge, inside the conductor, things start happening. The charges start to run around in there and say, ooh, I'm going to get away from that charge. I'm repelled by it, so I'm going to run to the other end of the object. Other charges will say, ooh, I like that charge. I'm attracted to it. So they'll run towards the object. So what happens is temporarily you polarize the object and it can now attract. Now, what example did I provide for this last week? I showed a slide where I took a plastic or amber rod, rubbed it on a piece of fur or carpet, and it charges the rod. And I can put the rod near paper scraps, which are uncharged. The paper scraps become polarized and will be picked up by the rod. I can do the same thing with a collection of paper clips because they're made of conducting material, mostly iron. And what I can do is first take a plastic or rubber rod, hold it near the paper clips, nothing happens. Because when there's no charge near the paper clips, their charges internally are evenly distributed. There's no attraction of electric pull between the rod and the paper clips as long as they're not charged. Now I take the rod and I rub it on a piece of fur, I rub it on a piece of carpet, and the rod rubs electrons loose from the fur or the carpet and becomes negatively charged. Now when I hold the rod near the paper clips, magically the paper clips jump. And they jump up onto my rod. They are attracted to my rod. They were not attracted before, but they are now attracted. That is because since I charged the rod negatively, negative entities in the paper clip say, I'm getting away. And they run to the opposite side from where the rod is approaching. Positive charge within the initially neutral paper clip say, I like that. And they move and migrate towards where that negative charge is approaching. So temporarily, the paper clips are, as we call it, polarized. And the temporary polarization allows them to be picked up. Now, electricity is not the only polarizing phenomenon. You are probably more familiar with this with magnets. Everybody knows that everybody here has a home or has been to a home with a refrigerator covered with magnets. Does that mean if I pick the refrigerator up and hold it near paper clips, it will pick up any nails on the floor or paper clips on the floor? No, the refrigerator is not a natural magnet. The refrigerator does not have magnetic character to it. Now it does internally, but it doesn't have a permanent magnetism associated with it. So what happens when I bring a magnet near it that I'm going to stick onto it? Of course, magnets stick all over it, but I am only temporarily magnetizing the fridge. Only under the spot where I've stuck my little "I've been to Rock City" magnet is the metal in the fridge polarized so that you've generated a little local magnet in that fridge. Same kind of thing I'm talking about with the paper clips and electricity. You can do with magnets on a non-magnetic metal. Not all, but many metals are non-magnetic and they will be attracted in that sense. Okay, now I'll have more pictures on magnets and their behavior. Maybe we'll get to it later today. Maybe we won't. We'll get to it eventually as I keep blathering and rambling along. What I'm showing in my picture on the left here is how charge field lines emanate from a positive entity I'm calling plus Q. In space, I draw like radial spokes of a wheel pointing outward from the positive charge. Now, why physicists have designated this as moving outward? This is repulsive, if you like. That's what you should be thinking. Not like the Earth. This is not a pull. This is a push. So why are we claiming positive charges push? The real claim is that this is decided if you pretend, as it says in the words above. Electric field lines are defined relative to the force that an imaginary positive charge would experience. So since there's a positive charge in the middle, if I bring an imaginary positive charge near this positive charge in the middle, it's pushed away. So we have deemed and decided field lines are going outward from positive. Now then, if the center is a negative charge, and again, I take a fictitious positive charge, bring it into proximity of that central negative charge, it will be pulled or attracted. So the field lines, as you can see, are absolutely reversed. They're in the complete opposite direction. So this is more like the behavior of gravity. If that central Q was the Earth, I would draw the field lines emanating from that central Q on the right as if the Earth would do, pulling towards its center. Now, notice I'm not deeming this to be a big hunk of matter. Usually our amounts of charge are such tiny amounts of matter you can't even really see them. But still, you should note all these lines are pulling towards the center of the positive charge. I'm sorry, scratch that. All these lines are pulling towards the center of the negative charge. All these lines are pushing outward from the center of the positive charge. Okay, now what happens with distance? Here's the magic formula, but I don't care so much about the formula. I just want you to know the relationship. The relationship says that E, let's put, if we were going to stick numbers in this formula, the distance of the away from that point charge is related, of course, in the R value. And the value or strength of the field is in the E value. And since R is in the denominator, or the bottom of the numeric expression, that means you divide by the distance. You not only divide by the distance, you divide by the distance squared. So if you go twice as far away, 2 times 2, which is 2 squared, is 4. And you're going to divide the field strength by 4. So again, if you pretend you're a distance r away, whatever r is, now move twice as far away, you're 2r away. But now since that value is squared, it's as if you're putting a factor of 4 in the denominator, so e is 1/4 as big. If you go 3 times as far away, you're putting a factor of 3r in the denominator, but it's 3r squared. 3 squared is 9. You have 1/9 the field. So the field strength, just like gravity, gravity does the same thing. The gravity field falls off at a proportion, inversely proportional to the distance away. Double the distance, you have 1/4 the gravity. Triple the distance, 1/9 the gravity. You go 5 times as far away, 1/25 the gravity. So if you go twice as far, well, I think I have little circles here. If you go a distance r away, you get a field E. You go a distance 2r away, you get a distance or a field 1/4 E. If you go 3r away, you get a field strength of 1/9 E. Now, the other thing to note is that this occurs on concentric circles. This is the same phenomenon that would happen with gravity. As long as you're the same r distance away, you can be anywhere on the edge of a dashed circle and still feel the same gravity effect. So the inner circle, we're claiming the very tiniest dashed circle in the middle, everybody standing on that circle would feel the same strength electric field. If you're on the middle dashed circle on this picture, which happens to be twice the distance away from the charge, you will feel a field 1/4. Everybody on that circle will feel that same 1/4 charge pull. And if you're on the outermost circle, which is represented there as being 3 times whatever distance r happens to be, you're triple the distance we started out away. Then because that factor of r is in the denominator and we're squaring it, and that denominator squared will put a factor of 1/9 in the problem. So E is over 9. I have 1/9 the field strength when I'm 3 times as far away. Okay, now let's just talk about what it means when the field lines are closer together or further apart. It's kind of nice how, notice here I have a bunch of lines coming outward from that charge. Notice the further away from the charge you get, just like the spokes on a wheel, the further the spacing is between the lines. The more spacing there is between field lines, what we can claim is that's weaker and weaker field. So if you get on the inner circle, there's a shorter distance between the lines coming out of the edge of that innermost circle. You go to the middle circle, notice between the lines, there's more space until you get from the first line to the second line. When you go on to the third circle and go around the curvature of that circle, there's even more space between the lines. If we put a fourth circle, there would be even more, and then on and on it goes. So there's some indication between the spacing between the lines and how much field is emanating from that charge. Now, what I'm trying to qualitatively show here is that I begin on the left with a charge Q. And this charge Q is positive. So the lines that are coming off of Q are outward. All positive charges have outward fields. And then on the right, I have a field 2Q. But now I have a field 2Q that is negative. All right? So on the left, I have positive Q. On the right, I have negative 2Q. So there are two differences between the way I represent the field strength pictorially without numbers. Notice there's not a number on there. You're given no numeric information about the field strength, but you're given pictorial information. Not only are you given pictorial information about the field strength, you're given pictorial information about the field direction. Notice how the lines are pointing outward from the positive and there's a decent amount of space between them. Notice since the charge on the right is doubled, the spacing between the lines is cut in half, if you like, for every one that, if you look at the pictures closely, you'll notice for every line on the left picture, there's just one bisecting the lines on the left picture. I just put one down the middle of it, each one of those little segments. There are double the field lines on the right compared to the left. Now, what again this is trying to indicate is there's double the field magnitude, because instead of Q causing the field on the right, 2Q is causing the field on the right. Now, of course, the other thing to note is that the lines are moving in instead of out. Now, what is then interesting is I'm pretending that charge Q1 and Q2, I'm sorry, charge plus Q on the left and charge negative 2Q on the right, they're not interacting and influencing each other. I'm pretending there's no influence on charge plus Q by charge negative 2Q. I'm trying to indicate by the way the lines are nice and straight that there's no influence on charge negative 2Q by charge plus Q on the left. What happens if the charges interact? If the charges interact, then the field lines don't radiate so nice and straight. They begin to curve and bend, either repelled by the neighboring charge or attracted to the neighboring charge. So let's just look at qualitatively again, no quantitative story, meaning don't worry about what the formula says. We're not going to put numbers into the formulas. Let's just look at what charges look like if there's more than one charge causing the field. Okay, so this is what a negative and positive charge, each of the same magnitude, will do to one another in terms of what their field starts to look like. Again, I'm going to back up. The picture before is claiming, notice how I kind of put a line down the middle. The line down the middle is saying that there's insulation between charge one and charge on left, charge on right. So there's no influence charge on left is exerting on charge on right. So now what I'm going to show on this slide is what happens when you remove the insulation between the two charges. Now they begin to affect each other. And what you should think of as what would occur is if you were moving a charge from left to right in the electric field generated by these two charges, they would follow along the arcs of these curves. That's how they would fly. A positive charge would be pushed away from the left positive along one of these lines. A positive charge would be pulled towards the right negative along these lines. So some of these charges would be following curves, arcing, depending on where they are in space. Now the ones on the left-hand side of the positive charge look like they're just going into nothingness. They're not connected. If my picture was big enough, you'd see they probably wrap all the way back around and come down onto the negative charge on the right. So the picture is limited in how the connection will be gained between the lines, but the ones that look disconnected out in space there would eventually, if the charges have enough field strength, they will eventually wrap all the way around and connect if given enough charge to cause their effect. Now, look, let's talk serious here. Do I expect you to be able to mimic and draw pictures of this type? We're not physics majors here. We're not here to do the kind of gore and detail like that. I'm just trying to give you an idea as, again, I'll back up one, compared to when they don't influence each other. Notice how the field lines don't bend. That's the key. If there's no external thing messing with a field strength, it has nice spoke-looking field lines. But when other charges can influence each other, then the field lines are perturbed by the presence of the other thing. Again, if you took the charge on the right away, then there'd just be straight outcoming lines from the charge on the left. If you took the charge on the left away, there'd be straight incoming lines on the charge on the right. But they influence each other to bend the field in the way that you see here. Now, of course, what this means is that cunning physicists can line charges up in space and create an electric field that has a particular shape to do something they want to do. Now, what would that be? Well, there's situations like in the old days, this is not so true anymore, but I hate to harken back to things that are really kind of old technology, but the good old TVs. And I think we all are familiar. We're not that young, I hope. I mean, have we only seen flat screen TVs in our lives? Maybe that's true. Could be. But we used to have TVs that were these big picture tubes, as we call them. And the picture tubes were streams of electrons that shot on the phosphors to make them glow all these colors. And we looked at the colors that were being shot onto the screen. It was pretty crazy technology when you stop to think of how they do that. They being pretty smart people. Well, of course, to get the picture to focus onto the screen meant that you had to curve massive amounts of charge to focus the picture onto the screen. So the design of the electric field is specific to make the images form on the charged surface so that we can see the image. So believe me, a lot of care has been taken into this simple picture I'm showing here for influencing the way a field behaves for just two charges. This has been perfected, if you like, by electronics engineers to make images be formed for a massive charges, or a massive charges to form an image. Okay, so let's just, here I'm going to just show a picture or two more. If I hit the right button here, this is what a charge that's twice as strong as another. This is kind of what the field lines would look like coming off of that. Again, maybe we should compare. These are two equal charges. Now in this picture, I have one massive charge compared to a less massive charge. Again, am I gonna give you two dots and say, draw me what the field looks like around all these charges? Nah, I'm not gonna do it. This is what a field looks like when the charges are the same. Now, again, I want to back up here and contrast. What's the contrast between this picture? These are opposite charges. Lines are coming out of one and going into the other. These are opposite charges. Lines are coming out of one and going into the other. Here, I have like charges. Turns out these are both positive. How do I know that? Well, it says plus. But besides that, the lines are all coming outward. But notice what kind of happens towards the middle. The lines start like ramming into each other and butting up against each other and pushing each other away. And notice another interesting point about the like charge area. Between the two charges is a dead spot. What we could claim there is there's cancellation of the field. And what does that mean? Remember, these are vector lines. The ones coming out of the ones on the left are heading to the right. The ones coming out of the ones on the right are heading to the left. They're butting into each other in the middle. And as we talked about, you add them if they're going in the same direction. You subtract them if they're going in opposite directions. So there in the middle, the vector lines of field from the charge on the left are canceling the vector lines of field from the right. Now, just as a point of interest, let's back up here and look at the difference as what goes on when the charges are opposite. Between them, you actually have reinforcement. Think of it, I have a push outward from the left positive charge. I have a pull inward from the right negative charge, those are working together. The field lines are intensified between the charges when they're opposite in the space between them, as opposed to when they're the same. Oops, that's not it. I went the wrong way. When they're the same charge, the field is canceling between them. Now, this would, of course, be true whether they are both positive charges or whether they are both negative charges. If I have equal negative charge minus q and minus q doing this picture, it would look exactly the same. The only difference would be that the arrows on every field line would just be turned upside down. Instead of the lines emanating outward from two negative charges, all the field lines would emanate inward towards the two negative charges. The positions of the lines, if the charges were equal, would be exactly the same. All right, now notice one thing I've been doing so far is showed all these nice, pretty, symmetric charges. What happens on a big hunk of matter? So the indication here is I just have little tiny amounts of matter that has charge permeating them throughout. What happens if you have a big chunk of matter? And we answered this question a little bit earlier. Remember I said if I take my rod and I rub some electrons off of it and then I touch a conducting object with it so that the electrons on the rod can be transferred to the conductor. They hop off onto the conductor, but now that they're on the conductor, they say, we're all the same, we don't like each other, let's push apart. So this is a large conducting sphere. The key of it being a conducting sphere, conducting means, and literally it means charge can migrate. Charge can move through the conductor. So even if I deposited the charge in the upper left-hand region of this sphere, essentially instantaneously, they run away from each other. They don't like each other because they're the same charge. And what they will do is literally run away from each other as far as they possibly can. So they will run away from each other to the outermost edge of the object. So when you charge any conductor, and it's a big conductor so that there's plenty of space for the charge to migrate, essentially instantaneously, all the charge will migrate to the outer edge of the conductor. Now, if you put a huge amount of charge, then they can make the air conduct. The air we're going to assume is a good enough insulator to not support the migration of charge, so the charge is stuck. Once it gets to the outer boundary of the conductor, it can't force the air to conduct. If there is sufficient charge, then what that means is there's sufficient voltage, air can be forced to conduct. And when do we see that? We've all seen that. Your mom and them have seen that. When have we seen that? Anytime you see a lightning bolt. In a lightning bolt, air has been forced to conduct. Believe me, the air doesn't want to conduct. So it takes a huge separation of charge, a huge pileup of charge to force the air to be a conductor. Okay, so we're pretending. Notice again, of course, also the base. The base of this sphere is obviously, based on the picture, is made out of a different material. The material in the base of this sphere is also an insulator. If it weren't, the charge would essentially instantaneously run out of there and into the ground. And this is what we call this. What does an electrician call it? We grounded the object. If you ground the object, you give the charge a path so that it is not localized. It will go into the ground and then as quickly as you can blink an eye, it will evenly redistribute again. So not only is the air an insulator outside the upper surface of the conductor, the brown looking thing on the bottom of the conducting material is also an insulator, which doesn't allow the charge to continue to migrate to the, as we like to call it, as electricians like to call it, we won't ground the object and allow the charge to get away from this conductor. Okay, so the charge then is piled up on the outer edge. So what happens if the charge is on the outer edge? Then we can just draw field lines from the outer edge. So field lines will emanate outward, just like we did for the little chunk of charge. I'm going to let field lines emanate outward from this big chunk of charge. But then that begs an interesting question, at least interesting to somebody like me. What about inside? What happens inside the conductor? Is there a field in there? Okay, let's be very clear about this. I don't care if this is hollow or solid. If it is hollow, obviously there's no charge in there. Because if it's hollow, it's filled with air. And of course, if it's hollow and filled with air, air is an insulator. If it's hollow and filled with air, there can be no charge in the center. It's all going to be in the conductor. So if it's a thin metal sphere that's mostly air on the inside, all the charge is in the metal. And the metal, if it's thin, has all the charge on the outside of the sphere, of course. What if it's a solid sphere? Well, if it's a solid sphere, then you'd have conducting metal in the middle. So let's say 10 or 12 charges decide, I'm going to get down in there. Then they get down in there and say, oh, I'm repelled by the other ones in here. I got to get as far away from them as I can. So the other ones run to the edge no matter what. Whether this is a solid sphere or a hollow sphere, the charges are on its edge. Okay, now I'm going to promise you, when you do my little practice problems or my little Moodle problems, one of the problems is going to quiz you about if this was a solid conductor and we charged it positively, would there be positive charge in the middle? Would there be negative charge in the middle? Would there be no charge in the middle? There's no charges in the middle. The positive charge, if you charge this positively, they all run to the outer edge. If you charge this negatively, they all run to the outer edge. Because they don't like each other, they repel as far away as they can. Now, let's then think, there's no charge in the middle. Is there a field in the middle? Okay, now remember what we mean. Just because there's no charge present doesn't mean that you can't be pushed or pulled by charges in other locations. Just like with the planets. We get pushed and pulled by the sun, and we're nowhere near the sun. The Earth gets pushed and pulled by the moon. And I explained that in terms of the tides on the surface of the Earth. They're solely an artifact of the pull of the gravity of the moon on the Earth. So strong, it pulls all the water towards it or away from it as the Earth spins and the moon moves around the Earth. There's this tidal action that comes about that has been going on for eons of time based on the gravity pull that the moon provides to the Earth. That occurs without the moon touching the Earth. So even though there is no charge in the center of this conducting object, whether it's solid or hollow, is there field? Or is there the ability to push or pull in the center of this object? To do that, we'll answer the question much like we did for the planet Earth by dividing the sphere into a bunch of little sections. So let's suppose I consider I have maybe, what is it, like 20, not even 20, about 16 or so positive charges distributed along the edge of this solid or hollow conductor. I don't care. Let's say solid, just for the fun. They still would all be on the outer edge because they're repelling each other as far away from each other as they can get. So let's just suppose the charge from the top is pushing on something in the middle. And of course, the charge from the bottom will be pushing on that same thing from the middle. But the charge from the bottom has a vector of push opposite in direction to the vector on the top. Okay? So these two will cancel each other. What about the ones from the left and the right? The one from the left will push away on that charge, trying to push it to the right. The one from the right will try to push away on that charge, trying to push it to the left. So these would be the directions of arrows that the pushes would be caused by those two. Then if we just do this same thing for all the other charges that are in there, notice we get a bunch of pushing arrows, all equal and opposite to one another. So careful analysis will show that there's no charge at the middle. Well, not only is there not charge at the middle, there's actually, believe it or not, no charge anywhere. Or I'm sorry, I shouldn't say charge. There's no field in the middle. There's no field anywhere in there. Doesn't have to be in the middle. I can move a little bit towards the left side and be closer to the left side charges than the right side. What it turns out to be is that there's more charges from the right influencing it then, but they're spread over a longer distance away. Again, they still cancel. So really you need some tricky calculus to prove. It's easy to see for the middle that this is true. I guess you'll just have to take from the word of faith of me that I've done this with some fancier mathematic tricks. Anywhere within the conducting sphere, what you find is there's no electrical field in there. That has all kinds of interesting ramifications. I thought I would have that picture. Let me show. Oh, there it is. There's the picture I wanted to show. And then I'll back up to the next slide after I do this one. This is the famous story of what results from there being no field inside the conductor. This is showing a dude, looks like a 1950s dude, in a car, and the car is getting struck by lightning. And I'm sure your mom and them have always said it's nice and safe to be in a car during a lightning storm. Well, that depends on what you're touching, to be honest with you. But let's suppose you're sitting on an insulated seat made out of plastic so that you're not touching anything that conducts very well. You've got your feet on a carpet. And believe me, it better be a pretty good carpet. But I have some shoes on, some good insulating soles. But let's just suppose, even though this car is this weird, irregular shape, you deposit charge on the car. Instantly, the charge runs to the outer edge of the car and gets as far away from you as it can, or from each other as it can. The car becomes charged with the charge of this lightning bolt distributed as far away from each other as they can get, all over its surface. If you do some calculus analysis inside there, these charges try to emanate field lines in there. Again, they're all going to come up so that they end up canceling each other. There's no electric field inside the cage of this conductor. This is called a Faraday cage, named after the scientist who described and discussed this, that inside any conductor, no matter what the shape is, even if the conductor is charged, inside there's no electric field, independent of the shape. Now, where might you have seen this in a movie? Well, I don't know how many movies you watch, but now a long time ago, probably as long ago as most of us have been alive here, except for me, Will Smith made a movie called Enemy of the State. And in the movie, Gene Hackman was this CIA agent who was a rogue CIA agent and the CIA was trying to get Will Smith in all this trouble over some dastardly deeds, and I'm not going to get into all the gore, but Will Smith and Gene Hackman go to his communications hub, and it's inside of a cage. It's not inside of a cage because of the fact it's for security reasons and keeping people out. It's in this cage because it's now surrounded by a conductor. And any incoming electricity will charge the cage, and there will not be a field inside. So very delicate electrical equipment is very often put inside of conducting cages so that any spurious external electric fields cannot affect the behavior of those entities within that cage. Another practical application of this is what is known as a coaxial cable. I'm not sure if you know what I mean by a coaxial cable. They don't have the usual two-prong plug. What they do is they have this little round thing with a little line sticking out of the middle, and it's got this metal thing around the edge, and you put into another thing, and you twist it a little bit, and you make the connection. Called a coax cable. The deal with the coax cable is that line down the middle is the real conductor that's going to carry your current for you. The outside of it is a cage of conductor that shields the line down the middle from any external, if anything comes down on it, it charges, but inside the coaxial cable, no electric field gets in. So that inner point thing is the conductor that doesn't have any influence from external electric fields that can add static to the sound, or if it's a low strength signal, prevent a low strength signal from being harmed from any other spurious electronic signals that are encroaching upon it. So anytime you use those bizarre looking cables, not with two prongs, but you twist together and kind of lock into place, if you look closely at them, the outside is a bunch of conductor. That really has nothing to do with anything. It's shielding that little thin line in the middle, which is what you're trying to protect inside the cage from any external fields acting upon it. Okay, now I'm going to back up here and show you, if you don't have a regularly shaped object, kind of like the car, it's not a regularly, symmetric spherical object, it's a kind of irregularly shaped object. What happens is that the charge can kind of pile up in bunched up areas. And if you notice, okay, look on the right, I have like a kind of a gradual curve. And then on the right of this object, I kind of have a flat spot. And this is a semi-solid conductor. It's partially hollow, but it doesn't matter whether it's partially hollow or all the way hollow. When I charge this thing positively, all the charge runs to the outside, and you'll notice the charge is bunched up in regions where there's like little nooks and crannies, like there's curved regions where the stuff can kind of bunch together. Then on the flat, smooth areas, the charges seem to be spread further apart. So anytime you get a little nook and cranny, you're going to have a region where a large amount of charge can gather, and you have strong emanating field from that. Anytime you get a smoother, flatter spot, there will be fewer charges gathering around that. And so the charge is not evenly distributed across the surface. Now, again, let me go back one more picture again. When the conductor is smooth and nice, regularly shaped, charge evenly distributes. When the object is irregularly shaped, charge is no longer regularly distributed. It bunches up in points where there's lots of curves and I don't know what we call it, where the irregularly shaped conductor is not very smooth, it bunches up. Okay, now where would you might see a ramification of something like this? Tell you where for sure. In your microwave. Your microwave has enough energy to make electrons run around. If you don't believe me, get a little fluorescent bulb and put it in the microwave and turn it on. Don't do it for long, but if you do it very briefly, the fluorescent light will light up without even being plugged in. And light a fluorescent bulb in a microwave with caution. Please do not leave it in there for any length of time because it'll probably blow up. So maybe you shouldn't even listen to what I said to do that, but it will work. Okay, so electrons can easily be made to move in a microwave. But if you put conductor in the microwave, I think we all know this. Don't put a fork in. Don't put aluminum foil in. Why? Those are conductors. In particular, a fork has tines. And the tines are piled up sections of conductor. And the piled up sections of conductor will get a lot of charge as you turn the microwave on and the charge begins to migrate. And then little sparks can happen between the tines of the fork. Same thing is true with aluminum foil. It's not so much the foil. If it's nice and flat, it's probably okay. But aluminum foil usually has kinks and dips and divots and points where it's all bunched up and crinkles and all this other stuff. That's what's trouble. The charge piles up in the crinks and divots and all that stuff, and enough charge builds up that you are going to build enough charge to make little lightning bolts in your microwave. So you got to be careful when you have weirdly shaped conductors that you even put in something such as a microwave. Okay, so that was the last slide of this part of this, but that doesn't mean that I am stopping there. We're going to start talking about our next bit of information with regard now not to charge in matter, but now with regard to the other phenomenon of great interest that is very similarly related. This is the cousin of electrical phenomenon. It is magnetic phenomenon. Now, in many regards, I would argue that you're more familiar with the behavior of magnetism than you are with the behavior of attracting charge, because we see it more often. We use it in a practical sense more often. So we use magnets ornamentally to do little cool things for us, to play little tricks, and actually to help us attach and hold things together. Of course, we also use magnets nowadays to store information. If you're not familiar with where you are storing information using magnets, I'm sure many of us swiped a card today, and if you didn't swipe one yet, you'll be swiping one later. Of course, when you swipe a card, what's being read on the back of the card is a magnetic strip. And the magnetic strip is coated with information in magnetic fields that can be read by the card reader to transmit information stored magnetically onto any other object that you want, or into an electronic form that we can transmit to your bank or whatever. We use magnets a lot in recording and amplifying our voice. And when we make a speaker, what is a speaker doing? It's just a magnified mouth. My mouth is able to push quantities of air to you. What is a speaker? It's a cone of cardboard and other maybe fancier materials, depending on how fancy the speaker is, that dances in the air and creates massive push of air, and of course can deliver huge amounts of sound in the air. Well, what makes the speaker dance? We all are familiar, I think, with the fact speakers are heavy. Why are speakers heavy? All speakers, I don't know of any other kind, all speakers end up having some type of a magnet in them. And it's the interaction between a little electrical current that creates another magnet. An electrical impulse makes a magnet that makes the magnet in the speaker dance. It either is attracted or pushed away from the current flowing into it. The current flowing into it carries the coded message of the signal you want to transmit. So it sends that signal out and makes the magnet dance. So there's all kinds of applications and uses of magnets. When we even use a microphone, we're speaking into something that's making a magnet dance and changing that into a current and encoding the information that it's carrying as well. So again, I would offer that probably without question, we're a little more familiar about the behavior in the use, or we more often use magnetism than we do electricity anyways. So what is magnetism? Well, the important thing with magnets, just like the important thing with electricity, is you can make a magnetic field. And it turns out that we can make magnets naturally, or we can make magnets electrically. Humans can generate their own magnets, and nature can generate magnets. So we're going to say a little bit about how nature can generate a magnet. We're going to say a little bit about how humans can generate a magnet. Okay, much like electricity, magnetic forces are either attractive or repulsive. So there are two flavors of magnetism, just like there are two flavors of electricity. Now, instead of designating them plus and minus, as Ben Franklin did for electricity, what they have been designated is, I think, familiar to us. We call the two actions of behavior magnetically either north or south. Now, really, today seems a little antiquated, but that's what we go with. So that's what we're going with. I mean, as a matter of fact, I don't know any other designation that scientists have argued should be used. We use north and south to designate the two different, uniquely different. Now, they're the same phenomenon, again, just like charge, they're just opposite direction. One will be a push, one will be a pull. Just like plus and minus could either push or pull. Now magnetic north or south can either push or pull. So obviously magnetism is a vector quantity, just like electricity was a vector quantity. It has a number associated with it, a sign of how much push or pull will exist. Or, I'm sorry, a number designating how much push or pull exists, but it also has a direction. Now, the north and south thing, of course, comes about by interaction with the Earth. Very simply. If you have a north magnetic pole, it points towards the North Pole of the Earth, quite simply. And the North Pole of the Earth is near the polar Arctic tip of the Earth. It's not at the very top of the Earth. And the south magnetic pole points near the South Pole of the Earth, which, again, it's not exactly at the South Pole of the Earth, near there. As a matter of fact, it moves, it's constantly moving. The North Magnetic Pole of the Earth and the South Magnetic Pole of the Earth are constantly moving. And right now, and pretty much for a long period of time, the North Pole has been close to the top of the Earth in the Arctic. The South Pole has been close to the bottom of the Earth in the Antarctic. Okay, so every magnet contains both a north and a south. This is certainly where we begin to see differentiation between the behavior of a magnet and the behavior of electric charge. You can isolate positive charge. You can isolate negative charge. Now keep in mind, you do pay a price. When something is positively charged, somewhere else, something is negatively charged, and vice versa. If you negatively charge an object, somewhere else in the universe, something is positively charged. The difference here with magnets is that you cannot separate a north from a south. Everything that is magnetic contains both a north and a south. And since it has these two, it must simultaneously have these two poles. We call it a dipole. Now, charge can be a monopole. A charge can be electrically negative and can be completely isolated and contained on its own as being electrically negative. A charge can be electrically positive with no negative in any section of that positively charged object. Everywhere throughout that object, it is positive. The main reason that is true is that this thing is going to be a conductor. And once it is positively charged, the positives get as far apart from each other as they can, so they evenly distribute throughout it. Same thing is true with the negative. Once it is negatively charged, they evenly distribute throughout it. Okay, but what we're claiming here is for magnets, if you do this, and I don't know why you'd want to, but take a magnet and cut it in half. You might think, well, of course it is true that when you have a bar magnet, or a horseshoe magnet for that matter, one end of the magnet will be what we would call the north pole of the magnet. One end of the magnet will be what we call the south pole of the magnet. But now if I get a laser, or I get a really tough saw, or I get something, a hacksaw or something, and I think I'm cutting the south pole separated from the north pole, it's not true. The one side of the thing I cut in half will now still be the north as it was originally, but now the back side of it will become a south, and vice versa. I cut loose, I thought I cut it right down the middle, so I cut off all the south pole of it, but now the other half of it will behave like a north pole. So you cannot isolate a magnetic monopole. Well, that sounds like one of my things I may ask you. You can isolate an electric monopole. Okay, so as in electricity, magnetic follow the rules that like repel like. So, meaning, if you put two south poles of a magnet in proximity to one another, they will exert force on one another. That force will accelerate the magnets. That acceleration has a direction, as does the force, and the force will be equal and opposite. So the magnet on the left pushes with force just as hard on the magnet on the right as the magnet on the right pushes on the magnet on the left. The direction of action of the pushes, you can see, are outward. The magnitude of the pushes are equal. The directions of the pushes are opposite. Same thing is true as on the picture on the right. I put two north poles in proximity to one another. The north poles repel one another, and you can draw a vector line of action for North Pole A compared to North Pole B. They will be equal in magnitude, indicated by the length of the arrows, opposite in direction, indicated by the point of the tip of the arrows. Now, of course, if I put norths near souths or souths near norths, I'm going to have attractive force. Now notice my arrows are, instead of pointing outward, they're pulling inward. Just like we saw, if I put a plus and a minus, I have attractive force between the opposite sides of the magnet. And as we talked about with Newton's laws, this is indication of one of Newton's laws of behavior of the universe. In particular, it's known as Newton's third law, which says that for every action, there is equal and opposite reaction. If the north pole of magnet A is pushed away from the north pole of magnet B, they're pushed equally hard and pushed in opposite directions. if the north pole of A is attracted to the south pole of B, they are pulled equally hard and pulled in opposite directions. Okay, now then, based on these rules, the Earth, I'm going to say that, we're going to come back to this, okay? Let's just save the statement at the bottom till I show a picture of that one. I promise I'm going to come back to that statement, but I'd rather do it in an upcoming slide with a picture. So how do magnets occur? Well, the simple rule of what a magnet is, it's charge in motion. Charge in motion is a magnet. Charge being plus or minus. Plus moving makes a magnet, minus moving makes a magnet. Now, what you could say is that plus moving in a certain direction makes the opposite pole of what negative moving in that same direction would make. Now, I will say this as well. If you move plus in one direction, it will make a north pole. If you move plus in the opposite direction, it'll make a south pole. If you move negative in one direction, it'll make a north pole. If you move negative in the opposite direction, it'll make a south pole. So charge moving makes a pole. That kind of makes a monopole, but it turns out that we can't isolate that. If you got charges moving in one direction in part of it, you're going to have charges moving in the other direction in the other part of it, and you're going to make both poles. You're going to end up with two poles. We just can't stop that from occurring. Okay, so charge in motion is a magnet. You must have plus and minus to have a magnet. Now, if the plus and minus are not moving, then you still have attraction, because plus attracts minus and plus repels plus. So stationary charge causes force. We call that, and this is why they use the word, folks, electrostatic. When it's electrostatic, that means you have charge that's not moving. If you have electrostatic, you can have electric attraction, but not magnetic attraction. I'm saying those words again because they may be important at some point. You can have electric attraction when charge is moving. You can't have magnetic. Sorry. Let me back up to the first point. If charge is stationary, they can still have electric attraction. If charge is stationary, you get no magnetic influence unless charge is moving. Now, if charge is moving, it can still have electric attraction. But charge moving can now also have magnetic influence. So charge moving allows both kinds of influences, electrical influence and magnetic influence. Okay, so magnets can be caused by charge moving. It doesn't matter if it's positive or negative. What it will matter is the kind of pole you're making, like I said. Now, another thing that we can then note is that if you have a current carrying wire, current is charge in motion. So anytime you have a current, you're making a magnet. And guess what? We've taken advantage of this for quite some time, making large electromagnets in a junkyard. Magnets you can turn off and turn on. You can make them magnetic to pick a car up from point A, haul it across, turn the current off, car falls. Because when the current is off, there's no charge moving, there's no magnet. All right, I'm sorry. I might be even a minute over. Sorry. Peace out. I'm definitely. Oh, sorry, I didn't mean to do that. I'm supposed to do it. I'm definitely. I wanted to finish see if I finished my electricity stuff. I did. It's posted, getting posted for sure.
Thank you.
You too. Take it easy.